Hi everyone! I hope you are all doing well and staying healthy. My name is Christina Fosheim-Hoag, and today I will be presenting a very influential paper by Leslie Lamport called Time, Clocks, and the Ordering of Events in a Distributed System. The paper was released in the July 1978 issue of Communications of the ACM, and it's had a huge impact on the field of distributed systems and how we think about distributed computation. Kind of as an aside, you may be wondering, well, how influential was it? Well, when I Googled this paper, you can see that Google says it has nearly 12,000 citations, which is crazy. It also won the Edgar W. Dijkstra Prize in Distributed Computing during the first year that the prize was awarded in 2000, which was over 20 years after the paper's initial release. In addition, the concepts outlined in this paper contributed to Lamport winning the Turing Award in 2013. So it's a pretty big deal. So here's the agenda for today. First, I will motivate the problem being solved with an example. Then, I will describe the concepts of happens before relation and logical clocks, and I'll finally show how these clocks can be used to implement a distributed system. Although the paper also touches on a method of synchronizing physical clocks, I will not be discussing it, both due to the time constraint of this presentation and because the concept of logical clocks is a novel and revolutionary concept that continues to be relevant today. So let's get started with some motivation. Imagine that you're an aspiring pilot who wants to give plane rides to people. You only have a limited number of seats on the plane, so you can only sell a certain number of tickets. So, you decide to set up a server to host a site to sell tickets to your friends. The server keeps track of who has purchased tickets and how many are left. When you have multiple requests come in, you serve the requests in the order that they arrive. So, if there's only one ticket left and two friends try to buy it, then the first person to submit the request will be granted the ticket and logged into the system, and the second person will be told that there are no more tickets available. So now suppose that your plane business has taken off, pun intended, and as a result you have created an airline with many flights, many tickets, and many clients. A single machine can no longer handle all of this load, so you decide to create a distributed ticket system. Now, each machine in your system keeps track of the remaining tickets and the owners of those tickets with local state, and machines communicate with each other via message passing. Clients can make requests to any of the machines in your system, and the request will be forwarded to all of the machines in your system so that they can update the state locally. You need all the machines to have the same information so that you don't sell tickets that you don't have or have an incorrect list of passengers. But this begs the question, if two requests come in to two different servers, then how do we know how to order these events? So the first idea that we will look at is to try to repeat what we did with a single machine, which is order events by timestamp. So for the example's sake, let's say that the true time in the space-time continuum is 12:05 and 1 second. However, keeping precise time is a pretty difficult feat, so all the clocks in our system have some error. In our example, the error is on the order of seconds, but in reality, the error is much, much smaller. So let's say that the first machine gets a request to purchase the last ticket and then forwards it on to the other two machines. Then it responds to the user saying that they've successfully booked the ticket. Then, shortly after, another request happens and comes into the second machine. However, because of the skew of this machine's clock, it appears that this event was supposed to happen before the first event. So if we wanted to order by timestamps, the machines would have to roll back their changes, complete this new request, and then replay all of the requests that happened after. This is clearly not ideal because now we've sold the same ticket to two different clients. And as this example illustrates, physical clocks can be inaccurate, so we need a better way of ordering events. That brings us to the happens before relation. And Leslie Lamport introduced this as a way to solve the problem of ordering events without using physical clocks. So the happens before relation, denoted by this arrow, is a relationship between two events where one event is ordered before the other, and the result of the execution reflects that ordering. In order for two events to have a happens before relation, they must satisfy one of three possible conditions. The simplest condition states that if two events, A and B, occur on the same process, and A comes before B, then A happens before B. So here we have an example with a single process that has three operations. finding a flight, checking available seats, and reserving a seat. Because finding a flight comes before checking available seats in the process's execution, we say that finding a flight happens before checking for available seats. By this same reasoning, we can say that checking available seats happens before trying to reserve a seat. The second condition deals with sending messages between processes. Specifically, if an event A is the sending of a message M, and the event B is the receiving of that message M on a different process, then A happens before B. Now we have two processes, and you can see that they're both sending messages to each other. And in both cases, the sending of the message, send message to get available seats, or send status, comes before the receiving of the respective message. The final condition specifies transitivity. That is, if A happens before B and B happens before C, then A happens before C. In this example, we can see that sending a message happens before finding a flight, and finding a flight happens before checking for available seats. Thus, sending a message happens before checking for available seats by transitivity. And this transitivity rule allows us to chain together events to form an ordering of events within and between processes. It's also worth noting that an event cannot happen before itself because that doesn't really have any meaning in the physical world. So using this happens before relation, we can obtain a partial ordering of events. While this is a good start, we would like a total ordering of events that all processes can execute all requests in the same order. However, there are some events that are not related by the happens before relation. These are called concurrent events, where A does not happen before B and B does not happen before A. And in order to create a total order, we need to find a way of relating these concurrent events. So an example of concurrent events can be seen here. You'll note that we have all these items in red, which have some ordering, and all these items in yellow, which also have some ordering. However, there is no causal relationship between any of the events in yellow and any of the events in red. You can't say that find all flights on Friday happens before find flights 1, 2, 3, or vice versa. We would like to totally order these events, and to do so, we will now look at the main innovation of this paper, which is logical clocks. It's also worth noting that they are called Lamport clocks after their creator. So logical clocks are an abstract way of assigning a number to an event. Each process has a clock function which assigns a number to any event that occurs in the process. And the clock function can be implemented using counters. So here we have 3 processes, each with a process ID. Each process also has a counter representing the clock. The question is, what properties should this clock have, and how can we increment the clocks to preserve the properties that we want? So if we want to create an ordering out of timestamps, we want the logical clocks to preserve the causal relationships that we've defined by the happens before relation. As a result, we have what is called the clock condition, which states that for any 2 events A and B, if A happens before B, then A's clock value should be lower than B's clock value. I think this is pretty intuitive, right? It shows us that we can order A before B with the clocks. So with the clock condition in mind, we can break down the behavior of the clock by what type of event it's assigning a value to. If the event is not a message being sent or received, then the clock just increments between successive events. That way, any events that happen later in the process execution will have a larger clock value than those that happen earlier in the process execution. For example, here we have 2 processes, 1 and 2, that have clock values 7 and 1 respectively. When an event occurs on process 1, the clock is incremented to 8. Similarly, when an event occurs on process 2, the clock ticks to 2, and then again ticks to 3 when another event happens. The more interesting case is when a message is sent from one process to the other. Because the sending of the message comes before the receiving of the message, the sending must have a smaller timestamp than the receiving. To ensure this, the process sending the message includes the clock value assigned to the event of sending the message. When the other process receives the message, it must then reconcile the 2 clock values it knows about, its own and the timestamp sent with the message. To make sure it upholds the clock condition, the receiving process makes its clock value the maximum of the 2 timestamps and then it increments it. To put this more concretely, let's look back at the same example. So now, let's say that process 1 would like to send a sync message to process 2. In the message, process 1 includes a clock value of 9, as this is the clock value for the sending of the message. When process 2 receives the message, it must take the maximum of 3 and 9 and then add 1. This results in process 2 having a clock value of 10. But the question is, what if process 2 did not choose the maximum value? What would that do? To see, let's imagine that the process 2 changed its clock value to 4 instead of 10. This clock value is okay for the ordering of events within process 2, right? Because add new event has clock value of 3, and receive message has receive message has a clock value of 4, so it preserves the clock condition. However, sending the message on process 1 happens before receiving the message on process 2, but the clock value for receiving the message is not larger than the clock value for sending the message. By not taking the maximum value, the process violates the clock condition, and thus the numeric ordering of events does not preserve the causal relationships that we know about. So, now that we've talked about how logical clocks work, we can use logical clocks to create a total ordering of events, denoted by this kind of bolder arrow here. Events are ordered by their clock value, and if there are ties, then they are broken by the process ID. So, A is totally ordered before B if and only if the clock value is smaller or the clock values are the same and the process ID is smaller. In the same example from before, we see that there are now many events with different clock values, and you can see that some have the same values like process sync and receive message, and some have different. So process sync is on process 1 and receive message is on process 2. So when the events are totally ordered, we'll order process sync before receive message. And here is the total ordering of events. So now that we've totally ordered events in a system using Lamport clocks, we'll create a distributed system to show kind of the application of this idea. We'll be implementing a distributed resource synchronization system that Lamport outlined in the paper. The system will consist of a fixed number of processes that all have access to a shared resource. The resource can only be used by one process at a time to avoid undefined behavior, and we would like to be able to grant access to the resource without using a centralized scheduling process. Our system additionally needs to satisfy the following 3 conditions. First, a process must release the resource before a resource can be granted to another process. Second, different requests for the resource must happen in the order in which they are made. And finally, all processes cooperate and eventually release if all processes cooperate and eventually release the resource, then every process should be granted access. In other words, there should be no starvation if everybody cooperates. So to achieve these goals, every process will have a local request queue that will keep track of the requests made for the resource. The queue will be ordered by increasing timestamp, and there will initially be a single item on the queue. The item will have a timestamp lower than all other processes' starting timestamps, and it will be a request from the process that is initially granted the resource. We will also make some assumptions about the messages that are being sent between processes. First, we will assume that when multiple messages are sent from one process to another, they will arrive in the same order they were sent. In addition, we will assume that a message will eventually be delivered to its destination. While these assumptions are not crucial, they are valid and they help to illustrate the point more clearly. So here's the visualization that we'll be using for this example. We have 4 processes, each with a process ID and a clock value of 1. Each process also has a local queue that is initialized with a single value denoting that process 1 has initially been granted access to a shared database. As process 1 interacts with the database, its clock value increases. We will now talk about the methods of requesting and releasing access to the resource. For simplicity, each step will be assumed to form a single event. To request a resource, a process will send a message to every other process requesting that resource. The request will also include the timestamp for the event and the process ID. The requesting process will then add their own request to their local queue. In this case, let's say that process 2 would like to access the resource. So it increments its clock value and sends a request to every other process. It also adds that request to its own queue. When processes receive a request for the resource, they add the request to their queue and send back a timestamped acknowledgement. This acknowledgement will be really helpful when a process is trying to figure out whether they have access to the resource or not. Back to our example, when each of the 3 other processes receives the message from process 2, they will add the request to their queues and then they'll send back an acknowledgement. Then process 2 will receive the message and increment its own clock value. When a process is ready to release a resource, it first removes its request from the queue and then sends a timestamped message to each process asking them to do the same. So once process 1 has finished using the resource, or in this case the database, it can release it so that the next process can interact with it. So it increments its clock and sends a message to the 3 other processes. When the process receives a release message, they simply remove the request from the queue. So we can see that when all the other processes get the message, they remove it. Now the question is, how do processes know when they have been granted the resource? Well, a process is granted the resource when the following 2 conditions hold. First, the process's request to access the resource must be at the front of the queue. This means that there are no other requests with a smaller timestamp. Additionally, the process needs to know that no other request could be at the front of the queue, or there's no other process that's trying to access the resource that has a smaller timestamp. To do this, it must receive a message from every other process where the timestamp of the message is greater than the timestamp of the request in the queue. Because timestamps are monotonically increasing, and we are assuming that we receive messages in the order that they are sent, if we receive a message with timestamp 10, there's no possible way that we will later receive another message from the same process with a timestamp lower than 10. Hence, if all messages have timestamps greater than the process's request, the process knows that it has the most recent request and can access the shared resource. Here, we have fast-forwarded it a little bit so that there are many requests and many more events that have occurred. But we know that process 2 has been granted the resource because it received these 3 messages from the processes after it initially sent the requests. Because 4 and 7 are both greater than 2, process 2 knows that none of the other processes have had a request with an earlier timestamp, so the process 2 is free to access the database as it likes. I will finish the discussion of Lamport clocks with some pros and cons. Clearly, one of the biggest pros is that a complex distributed system can be implemented using a relatively simple algorithm by creating a total ordering of events using Lamport clocks. However, the distributed system we created has two big flaws. One is that it requires knowledge of every server, and it also requires participation from every server, since the processes can only progress once they know that the timestamps of all of the other processes are larger than its current one. If a server is down or cannot communicate with other processes because of a network partition, the system will not be able to progress. To create a system with a higher tolerance for faults, you should look into primary backup replication or Paxos, which is also written by Lamport. So to summarize, we talked about ordering of events in a distributed system. The happens before relation allows us to create a partial ordering of events, and using this idea, Lamport clocks provide a method of totally ordering events without using wall clocks. Finally, as we saw, you can use Lamport clocks to implement a distributed system. This concludes my presentation, and I thank you all so much for watching.